Hello everyone. Today we'll go through the basics of Label Distribution Protocol, LDP. After completing this course, you will have developed an understanding of the basic concepts and working mechanism of LDP, basic MPLS LDP configuration, and the MPLS label distribution control modes, advertisement modes, and retention modes. This course consists of 4 parts, and we will begin with the first part, LDP Basics. In the figure, we can see that R3 directly connects to network segment 3.3.3.0/24 and runs a routing protocol to advertise the network segment route to R2. R2 then forwards the network segment route to R1. After LDP is configured on each device, an LDP peer relationship is established between R1 and R2, and between R2 and R3. R3, as the downstream node of this topology, assigns label 1033 to FAC 3.3.3.0/24 and sends an LDP label mapping message to advertise this label to R2. R2 repeats this process by assigning label 1022 to FAC 3.3.3.0/24 and sending an LDP label mapping message to advertise this label to R1. This process establishes an LSP from R1 to network segment 3.3.3.0/24. Before we get started, we got to know some LDP concepts. An LDP peer relationship compromises 2 LSRs that have established an LDP session and use LDP to exchange label mappings. LDP sessions are classified into local and remote sessions. A local LDP session is established over a local LDP adjacency whereby 2 LSRs are directly connected. A remote LDP session is established over a remote LDP adjacency whereby 2 LSRs are either directly or indirectly connected. Every LSR running MPLS must have a unique LSR ID in an MPLS domain, which is 32 bits long and has the same format as an IPv4 address. In most cases, a loopback interface address of a device is used as an LSR ID. Every LSR running LDP must be assigned an LDP ID in addition to an LSR ID. An LDP ID is 48 bits long and consists of a 32-bit LSR ID and a 16-bit label space ID. The format of an LDP ID is LSR ID label space ID, for example, 2.2.2.2:0. A label space ID can be 0 or a non-zero value. The value 0 indicates device or platform-based label space. Such space is used on LSRs in this course. A non-zero value indicates interface-based label space. Before we dive into the process of establishing an LDP session, let's understand what an LDP transport address is. 2 LSRs establish a TCP connection using their transport addresses. The transport address of an LSR is carried in an LDP hello message and sent to an LDP peer. Hello messages are exchanged to identify one another as a peer and obtain each other's transport address. Once the transport addresses are obtained, they are used to perform a TCP 3-way handshake and exchange both LDP initialization messages and label mapping messages. Each message contains the transport addresses of the 2 LSRs as the source and destination IP addresses. Additionally, each LSR must have an available route to the transport address of the peer. By default, the LSR ID of device is used as a public LDP transport address, and the primary IP address of an interface is used as a private LDP transport address. LDP uses 4 types of messages: discovery, session, advertisement, and notification messages. Discovery messages, including hello messages, are used to advertise and maintain the existence of LSRs. Session messages, including initialization and keep alive messages, are used to establish, maintain, and terminate sessions between LDP peers. Advertisement messages are used to create, change, and delete fake label mappings. Notification messages are used to provide suggestions and error warnings. Usually, discovery messages are transmitted over UDP, while session, advertisement, and notification messages are transmitted over TCP. Now, let's go through the process of establishing a local LDP session. Phase 1 involves LDP peer discovery and TCP connection establishment. The two LSRs periodically send LDP link hello messages to discover LDP peers. LDP link hello messages are UDP messages with destination address 224.0.0.2, which is a multicast address. If an LSR's interface receives an LDP link hello message, an LDP peer is connected to that interface. The hello message carries transport addresses, which will be used to establish an LDP session. The party with a larger transport address plays the active role and initiates a TCP connection request. In this example, R2 has a larger transport address than R1, and therefore R2 initiates a TCP connection request. After the TCP three-way handshake is complete, a TCP connection is established. Phase 2 concerns the establishment of the LDP session. After the TCP connection is established, R2, which has a larger transport address, sends an LDP initialization message to negotiate parameters for an LDP session. LDP session parameters include the LDP version, label distribution mode, keep alive hold timer, maximum PDU length, and label space. Once R1 receives the initialization message and accepts the parameters sent by R2, it replies with a keep alive message. To improve transmission efficiency, R1 also sends its own initialization message. This process is repeated after R2 receives the initialization message from R1. An LDP session is established when both ends receive the keep alive message from each other. After the LDP session is established, both ends send label mapping messages to advertise a label mapping. The label mapping message contains the mapping between a flag and a label allocated by a device. RFC 5036 describes the LDP State Machine. An LDP device is initially in the non-existent state. After TCP connection is established, an LDP device enters the initialized state, which then enters the open send state once an initialization message is sent. After receiving an initialization message, the passive party enters the open rec state and sends initialization and keep alive messages to the active party if the parameters are acceptable. If the active party accepts the parameters in the received initialization message, it sends a keep alive message to the passive party. After both ends receive keep alive messages from each other, an LDP session is established. In this case, the LDP devices enter the operational state. You can also refer to the diagram for the LDP state machine to see what may happen in the life cycle of an LDP session. In the LDP working process, first, a dynamic routing protocol such as OSPF is deployed to enable devices to discover routes to each network segment on the entire network. Next, MPLS and LDP are enabled on the devices and the corresponding interfaces on each device. This then leads to LDP sessions being established between directly connected devices. R4 is directly connected to network segment 10.1.1.0/24 and is the egress node. LDP running on R4 proactively allocates label 1041 to the root destined for the network segment and advertises the label mapping to all peers, including R2 and R3. Taking R2 as an example, in its routing table, the next hop of the route 10.1.1.0/24 is R4. When R4 receives a label mapping message for the route 10.1.1.0/24 from a downstream LDP peer, R4 allocates label 1021 to the route and advertises the related label mapping message to an LDP peer, for example, R1. The same process applies to R3. After receiving the label mapping of route 10.1.1.0/24 from R2 and R3, R1 stores the information and advertises label 1021 to R2 as its next hop. If R2 is unreachable, the OSPF route reconverges. In this case, R1 switches the next hop of route 10.1.1.0/24 in the routing table to R3 and uses the label advertised by R3. Finally, an LSP is established on R1 for the route or FAC 10.1.1.0/24. When R1 receives an IP packet destined for 10.1.1.1, R1 searches its FAB for the destination IP address of the packet and obtains an matching tunnel ID. If the tunnel ID is not 0, R1 forwards the packet based on a label. Then R1 continues to search the NHLFE table based on the tunnel ID and determines that the IP packet needs to be sent along an LSP. According to the NHLFE entry, the outbound interface is GE1/0/0. The label operation is push. The next hop is R2, and the outgoing label is 1021, which is added to the packet before being forwarded. During the forwarding of the labeled packet, the outgoing label used by a local device is always the label advertised by a next hop LSR. The basic working process of LDP is as follows. An LSR runs an IGP, such as OSPF or ISIS, to generate entries in the routing table and FIB. The LSR runs LDP to allocate a label to each route prefix in the routing table in the specific label distribution mode. The LSR runs LDP to advertise the label to an LDP peer through an LDP label mapping message in the specific label advertisement mode. The LSR stores both the label allocated by itself and the label advertised by its LDP peer for the route prefix and associates the two labels. When the LSR forwards a labeled packet destined for the network prefix, the LSR always uses the outgoing label advertised by its downstream LDP peer. The downstream peer here is at the next hop to the destination network in the routing table. Let's now move on to some enhanced LDP features, such as PHP and Null labels. LDP configuration is a relatively straightforward two-step process. Step 1. Configure routing protocol. In this example, OSPF is configured on R1 through R4 to implement network-wide route networking. The configuration is not provided here. Step 2. Enable LDP. In this example, MPLS and LDP are enabled on R1 through R4. The IP address of loopback 0 is used as an LSR ID. And that's all you need to do for the configuration process. Next, let's talk about some enhanced LDP features, such as PHP and Null label. In the figure, after receiving a labeled packet destined for 1.1.1.3/32, R3 searches the ILM table for a label. It then removes the label, searches the fib for the destination IP address of the IP packet, and forwards the IP packet, meaning R3 must perform a query operation twice. Can the forwarding efficiency of R3 at the last hop be improved? The answer is yes. The label of value 3 is called an implicit null label. If a penultimate hop LSR finds that the outgoing label value is 3 after label swapping, the LSR removes the label and forwards the packet to the last hop. Once the packet is received, the last hop either directly forwards the packet over an IP route or on the next layer label. MPLS forwards packets through LSPs. At the last hop of the LSP, the MPLS label of the packet needs to be removed first, and then IP forwarding or next layer label forwarding is performed. However, the MPLS label becomes not needed on the last hop of the LSP, and it can be removed at this stage. Therefore, the penultimate hop popping feature can be used to improve forwarding efficiency. In the figure, if R3 has PHP enabled, a special label is assigned to the local direct route 1.1.1.3/32, which is referred to as an implicit null label of value 3. R3 advertises label 3 to R2. Once an LSR received the label packet and it finds that the outgoing label corresponding to the incoming label is 3, the LSR removes the label from the packet and forwards the encapsulated data to the downstream LSR. In this way, penultimate hop popping is performed. At the penultimate hop to 1.1.1.3/32, R2 receives the labeled packet destined for 1.1.1.3 and discovers that the label value is 3. Therefore, R2 removes the label and forwards the IP packet to R3, which then queries the fib to obtain forwarding information and forwards the packet onwards, improving forwarding efficiency. Using the implicit null label can be problematic. An MPLS label contains information such as EXP, BOS, and TTL values, in addition to a label value. Among them, the EXP value is used for traffic classification and queues implementation. After PHP is enabled, the penultimate hop removes the MPLS label and the EXP value. As a result, end-to-end queues cannot be implemented. To ensure that end-to-end queues information is not lost, R4 requires R3 to carry queues information in a label, and therefore an explicit null label can be used. After the explicit null label is configured on R4, R4 advertises the label mapping for FAQ 4.4.4.4/32 to the upstream R3 with the explicit null label of value 0. If R3 finds that the outgoing label is 0 before forwarding a labeled packet, it replaces the existing label with 0 instead of removing the label. This ensures that the QC information in the original label is saved. In conclusion, LDP distributes the following types of labels. 1. Implicit null label 3, which is used for PHP. 2. Explicit null label 0, which can carry EXP information to implement end-to-end queues. 3. Regular labels whose value is greater than or equal to 16. In this case, PHP is not supported. Moving on, let's take a look at the MPLS label distribution control modes, notification modes, and retention modes. Before we dive into more detail, let's review the concepts of upstream and downstream. These two concepts are described from the perspective of data forwarding directions, whereby the device that sends data is an upstream device, and the device that receives data is a downstream device. As shown in the figure, for an LSP to 3.3.3.3/32, R1 is the upstream device of R2, and R2 is the upstream device of R3. Vice versa, R2 is the downstream device of R1, and R3 is the downstream device of R2. Let's look back at those three concepts. The label advertisement mode refers to the mode in which a downstream device advertises labels to upstream devices. In an MPLS system, a downstream LSR determines to allocate a label to a specified flag and then notifies the upstream LSR. That is, the label is specified on the downstream LSR. The label is allocated from the downstream LSR to the upstream LSR. The label distribution control mode refers to the mode in which an LSR distributes labels during the establishment of an LSP. The label retention mode refers to the mode in which an LSR processes label mapping that is received but is not currently needed. Upstream and downstream LSRs that have label distribution adjacencies must use the same label distribution mode, and these come in two modes: downstream unsolicited, or DU. An LSR distributes a label to a flag without having to receive a label request message from its upstream LSR. Downstream on demand, or DOD. An LSR distributes a label to a flag only after receiving a label request message from its upstream LSRs. There are two label distribution control modes. Independent mode. A local LSR can independently distribute a label to a flag, bind the label to the flag, and then advertise a label mapping to the upstream LSR without waiting for a label distributed by the downstream LSR. Ordered mode. An LSR advertises the mapping between a label and a flag to its upstream LSR only after either receiving a label mapping message sent by the next hop for the flag, or when the LSR is the egress node of the flag. A label mapping received by the LSR may be sent by a next hop or a non-next hop. Accordingly, there are two label retention modes. Labeler mode. An LSR retains label mappings sent by peer LSRs, regardless of whether the peer LSRs are the next hop of a flag. Conservative mode. An LSR retains a label mapping sent only by the peer LSR at the next hop of a flag. When the next hop peer LSR is changed due to a network topology change. In labeler mode, the local LSR can use a label sent by a non-next hop peer to re-establish an LSP, consuming more memory and label resources than in the conservative mode. In conservative mode, the label LSR retains the label advertised only by the next hop, which conserves memory and label resources. However, LSP re-establishment will be time-consuming. The conservative mode is usually used together with the DOD mode on LSRs with a limited label space. A label distribution control mode, label advertisement mode, and label retention mode can be flexibly combined. Currently, Huawei devices use the default combination of the DU, ordered, and labeler modes. And that's all for this course about LDP basics. See you next time.